Now we're going to look at a number of molecules drawn in Kekulé structure. We've seen Lewis structure being used with different shapes and different colors for different electrons associated with different atoms, hopefully making our life easier. In this case, we don't have that information in the same way, but the calculation will still work. So we need to work out the formal charge here. Let's look at a molecule called dimethylsulphoxide. And initially, we're going to focus on the oxygen. What is the valence electron generally for oxygen? The answer is 6. Now we need to look at this specific atom in this specific molecule. Firstly, observe the number of bonds. Here we have one bond. Half the number of bonded electrons, well, there are 2 electrons in that bond, so half that number is 1. Now we move on to look at the number of lone pairs. Here we have 3 lone pairs, and there are 6 electrons associated with those lone pairs. So the calculation we do is the number of valence electrons minus half the number of bonded electrons minus all the lone pair electrons. That's to say, in this case, 6 minus 1 minus 6. So overall, the answer is minus 1. This oxygen has a formal charge of minus 1. Next, we're going to look at sulfur. Now, sulfur is in the same group in the periodic table as oxygen. And so sulfur has valence electrons of 6. Looking at this specific sulfur in this molecule, we can see that we have 3 bonds. Therefore, are 6 electrons associated with those 3 bonds. Half the number of bonded electrons is 3. Now we look for lone pairs. There's 1 lone pair, and there are 2 electrons in that lone pair. So the calculation we're doing here is 6 minus 3 minus 2. And so the answer is plus 1. This specific sulfur has a formal charge of plus 1. Now sometimes we vary how we draw a molecule, and very often organic chemists are quite lazy, and so we don't draw everything a lot of the time. You'll notice in this new way of drawing the same molecule, we haven't put the letter C for a carbon, and we haven't drawn the hydrogens. This becomes useful when you're drawing very complex molecules and you're trying to cram in a lot of bonds and a lot of atoms into a small space. You need to get used to this abbreviation. As you learn more and more, this is the very, very common way for everything to be drawn. Our next molecule, we're going to look at the nitrogen on the right-hand side. Now, first question, how many valence electrons for nitrogen? That answer is 5. Now we want to look for the number of bonds. We have a double bond. That's like saying 2 bonds. So there are 4 electrons, half the number of bonded electrons is 2. Lastly, we're looking for lone pairs. There are 2 lone pairs and 4 electrons associated with those lone pairs. So overall, the calculation is 5 minus 2 minus 4 to give us the answer minus 1. This nitrogen has a formal charge of minus 1. Now we're going to look at another nitrogen in another molecule. So still the number of valence electrons is 5. That remains constant. But obviously the number of bonds and the number of lone pairs could have changed, and indeed it has. Let's look at this specific case. Well, here we have 4 bonds to the nitrogen. That's to say 1 triple bond and 1 single bond. There are 8 electrons associated with those bonds. So half the number of bonded electrons is 4. Now we need to look for lone pairs. In this case, there are no lone pairs. So we are left with a calculation of 5 minus 4 equals plus 1. This nitrogen has a formal charge of plus 1. And finally, we'll look at the oxygen on the right-hand side. So, valence electrons for oxygen, still the same, it's 6, right? Never changes. What about this specific atom in this specific molecule? How many bonds? Well, you'll see there's 1 bond, which has 2 electrons, so half the number of bonded electrons is 1. What about lone pairs? Well, there are 3 lone pairs which have in total 6 electrons. So the calculation we're going to do is 6 minus 1 minus 6 to leave us with a result of minus 1. This oxygen has a formal charge of minus 1.